Yes, questions? Okay, so if you remember yesterday we had kind of finished, we had studied what's called the Bose-Einstein condensation, and today we will be doing more or less the same things for fermions. And if you remember from yesterday, we had we basically started with the logarithm of the grand partition function. This is equal to the logarithm of 1 plus z e to power minus beta epsilon. Well, if you remember for the case of the bosons, this was a minus, this was also a minus sign. Now for the fermion, there is a sign difference, and although it seems at this formally quite a very minor change, it will have some important consequences. And this was equal to PV over KT in general, the logarithm of the grand partition function, and the number of particles we have is given as the average number of particles in a given single particle state, and this turns out to be sum over 1 over z minus 1 e to power beta epsilon. In the case of the bosons, this was a minus 1, but now for fermion, this is a plus 1. Now, since the average number of particles in each microstate should be larger than 0, larger than or equal to 0. In the case of the bosons, we had the constraint that z minus 1 e to power beta epsilon minus 1 should be greater than or equal to 0. And which basically told us that mu should be less than or equal to 0. So there was a constraint on the chemical potential. And since z was e to the power beta mu, this constraint means that z was between 0 and 1. If mu is 0, z is 1. If mu goes to minus infinity, or beta mu goes to minus infinity, then z is 0. But now in the case of fermions, our condition is that the condition on the number of particles is that e to power beta epsilon plus 1 should be larger than or equal to 0. But since beta epsilon is larger than or equal to 0, z is larger than or equal to 0, so this condition is always satisfied whatever the value of z is. The only constraint we have is since z is e to the power some positive number, some real number, sorry, not positive or negative real number, z is larger than 0, but it can take values up to infinity. There's practically no upper limit on the value of z. Now, of course, the analytical expressions in general will be difficult, so we will be basically looking at various limits. Now, let's look at what is z. You see, the z is determined by this condition over here. So n should be equal to sum over all single particle states of 1 over e to the power beta epsilon z to the power minus 1 plus 1, and so we can just convert it to an integral. This is equal to the epsilon, a epsilon 1 over e z to the power minus 1 e to the power beta epsilon plus 1, whatever the value of z is, z or the temperature is. Now, if you look at the large T temperature limit, well, we know that z is much smaller than 1. Essentially, it will go to 0 in the large temperature limit. So we can make a Taylor expansion, just like we did in the case of the bosons. Now, let me just look at what n was, what this a epsilon was. Well, sum over these single particle states would just give me, okay, there is the volume element, there is the momentum integral, there is 4 pi from the angular integration of the momenta, then we have p squared dp divided by h cubed. Well, there is a factor g due to the possible degeneracy in the energy levels. And at least if we are looking at fermions, they have spin, definitely they have spin. So if they are spin 1/2, this g would be just 2. So g is typically 2s plus 1. And then we have 1 over z to the power minus 1 e to the power beta epsilon plus 1. We will make, as in the case of the bosons, we will make several changes of variables. The momentum in terms of the energy, if it is non-relativistic, this is square root of 2m epsilon. dp is equal to square root of 2m over 2 epsilon. And if we make another change of variable and call beta epsilon as x, then this is just equal to n becomes g times v over lambda cube. The epsilon is to the power 1/2, no, dx, sorry. The x to the power 1/2 divided by z to the power minus 1 e to the power x plus 1. And as usual, this lambda is the so-called thermal wavelength. It is h over 2 pi m kt to the power 1/2. So x goes from 0 to infinity. And so we have this, well, this equation, if we write it in the form n lambda cubed over v, let me put the g over here, this should be equal to f 3/2 of z. So here, let me add the factor 1 over gamma 3 over 2. Now, these f functions for n z, they are defined as from 0 to infinity dx x to the power nu minus 1 divided by z to the power minus 1 e to the power x plus 1 and 1 over gamma of nu. You see, in the case of the bosons, we had a g function, the bosonic function, and then that g had that instead of plus 1, it had the minus 1. But basically, it had more or less the same form. And, okay, for small z, we can make an expansion, and if you make an expansion of this, this just turns out to be z minus z squared over 2 to the power nu plus z cubed divided by 3 to the power nu plus minus z to the 4 divided by 4 to the power nu, etc. Well, almost like the expansion of the g function, the only difference being this alternating sign. Do you remember how we obtained this expansion? Yes, it was basically, we just expanded around z is equal to 0. So we had a sum, and each one of those sums, it was proportional to gamma nu, so it canceled the gamma nu's, and we are only left with 2 to the power nu, 3 to the power nu, etc. So you see, this equation tells us that, okay, for a fixed volume per particle, that is that small v over there, and at high temperatures, remember lambda is proportional to 1 over T, at high temperatures, the right-hand side is a very small number. And if you would plot this f of 3/2, well, Mathematica would help us. You see, this is what f 3/2 is, how it looks like. It's a monotonously increasing function of z. So, okay, for the case of G, it was kind of obvious that all of the terms was monotonically increasing as a function of Z. In this one, there is the alternating plus minus sign, but still f of Z is a monotonously increasing function of Z. And from this figure, you can also right away see that small values of this f3 half of Z means that the value of Z itself is small. So although before I claimed that the large temperature limit corresponds to small z, here this is the proof. Now, like in the case of the bosons, let's just look at the, in the strict large z limit, this tells me that f3 halves of z, which is approximately z, this is just lambda cube over g times v. Then we can look at the pressure of this system at large temperatures. Well, you see the pressure is given by this expression over here. So this tells me that P over KT is just nothing but dp d cube p, no, let me just, dp p squared logarithm of 1 plus z e to power minus beta epsilon. And I have 4 pi over h cubed. And again, I do the same things. I call p is equal to square root of 2m epsilon, and beta epsilon is equal to x. And so this p over kt becomes, well, you see this integral is almost the same as the integral we have over here. So this is g lambda cube dx x to the power 1/2 logarithm of 1 plus z e to the power minus x. No, g over lambda cube, sorry. Now we can do an integration by part. X to the power 1/2 is just a derivative of x to the power 3/2 divided by 3/2. And if you just do the integration by part, etc., you obtain that this is equal to g over lambda cube. Again, the same f, this time 5/2 of z. Now this is valid for any temperature, for any z. Now for high temperature limit, well, you see basically the definition of the high temperature limit is that V over lambda cube. You see at high temperature lambda is very small, so this should be much, much larger than 1. This is the definition of the high temperature limit. Now P over KT is just g over lambda cube times z. Now because f 5/2 of z is also equal to z plus z squared over 2 to the power 5/2 plus etc. So at high temperature z is very small. We had already derived z is lambda cubed over gv. So z is very small, so that we can just keep the first term. So this is equal to g over lambda cube over g times v. Well, these cancel, lambda cubes cancel, and we are left with p v over n kt. This is equal to 1. Well, we just recover the classical result.
Where is n? Where is n?
You see, v is equal to v over n. So this v over n is our small v. We just recover the classical ideal gas. Now, of course, it will be interesting to get the first correction to this one, just like we did in the bosonic case. So to obtain the first correction, well, we basically need to keep the z squared term over here in f5 of z. And also, when we are finding z, we also need to keep the z squared term over there. Let me just call this thing delta to calculate the first correction. So delta is equal to z plus z squared over 2 square root of 2, no, minus, plus terms of the order of z squared, z cubed. I will be basically repeating what I had done yesterday. Now the only difference will be this minus sign. And now I can say that z is equal to delta. I know that when delta is very small, z is equal to delta. Or if you want, but maybe the coefficient will be different. Let me call this b1 plus b2 delta squared plus terms of the order of delta cube. So if I put it above, then delta turns out to be b1 of delta plus b2 of delta squared minus b1 squared of delta squared plus terms of the order of delta cube for all delta. Well, the coefficient of delta on both sides is 1 on the left-hand side, b1 on the right-hand side, so b1 is 1. The coefficient of delta squared on the left-hand side is 0, on the right-hand side it is b2 minus b1 squared. Now here I have 2 square root of 2, b1 squared over 2 square root of 2. This should be 0, so this just tells me that b2 is equal to 1 over 2 square root of 2. Well, in the case of the bosons, this was with a minus sign. So then we know that z is in parentheses of delta. b1 is 1, b2 is 1 over 2 square root of 2 delta. And delta is lambda cubed over g. Well, then we have what the pressure is. This is equal to g over lambda cube. If 5 half z is z minus z squared over 2 to the power 5 halves. This is equal to g over lambda cube. Well, z is delta, 1 plus 1 over 2 square root of delta, minus 1 over 2 to the power 5, let's say 4 square root of 2 times delta squared, plus there are term corrections of the order of delta cube. This is g over lambda cube and keep in mind delta was a v over g lambda cube, right? Lambda cube over gv, sorry. So here, this expression is just v over delta. No. Instead of 1 over lambda cube, we have the 1 over delta gv, 1 over delta v. I have this delta term, this is the first term, this is the classical result. And then I have plus, I have 1/2 square root of 2, then minus 1/4 square root of 2. The difference is minus 1 over 4 square root of 2 delta squared. Well, these, one of the deltas cancel. And we end up having PV over NKT. This is equal to 1. No, this is plus, sorry. 1/2 minus 1/4 is plus 1/4. 1 plus 1 over 4 square root of 2 delta is lambda cube over g times v plus corrections of the order of lambda cubed plus gv squared. By the way, I had said a mistake. Only yesterday I said that z was the virial expansion, but this is called the virial equation of state. Now, in the case of the bosons, at large temperature, at least when we take into account the first correction, we had seen that the pressure of the bosonic gas is slightly lower than the pressure of the ideal gas, and we interpreted it as a quantum mechanical attractive force between the bosons. There's no force. If you just take two particles, there's no force, but due to their bosonic nature, they tend to accumulate at the same point. So that was what we had called an effective quantum mechanical force. In the case of the fermions, there's again a quantum mechanical effective force, but this time, since the fermions cannot be in the same state, this force is repulsive, not attractive. So due to that repulsive force, it was natural to expect that the pressure should be larger than what it would have been if there were no such a repulsive force, and that is actually what we obtain over here. The pressure PV over NKT for a fixed V, N, and T, the pressure is higher than what we would have obtained for an ideal gas. Now let's look at the energy of the system in this limit. Now the energy, the internal energy, was given by minus the logarithm with respect to beta of logarithm of Q at constant Z and V, or this is minus the derivative with respect to beta of PV over KT. Well, let's see, we had already we have what PV over KT is. This is equal to minus, well, let me convert it to a derivative with respect to temperature. Times the derivative of the temperature with respect to beta. Of N times 1 plus 1/4 square root of 2 lambda cubed over GV plus etc. No, sorry, this is not the correct result. Why is this wrong? If I use this expression for PV over KT, when taking the derivative, I would have done a mistake. Why? You see, when I'm taking the derivative with respect to beta, I have to keep z constant. In this expression, I have already expressed z in terms of t and v. So there's no way I can keep the z constant when I'm differentiating this expression. So that would have been my mistake. So let's go back to the original expression for q. You say, this is my expression for q. Let's multiply this by v, logarithm of q. Derivative with respect to beta at constant z and v. Now the only place where beta appears is that lambda q. Remember, lambda q, lambda is h over 2 pi m kt to the power 1/2, or h over 2 pi m to the power 1/2 beta to the power 1/2. So this g over lambda q is proportional to beta to the power minus 3/2. Now this is the only part that depends on beta at fixed z. And so that derivative would just bring down a factor 3/2 beta. And then the rest is what? G over lambda cube f 5/2 of z. This is my u.
I guess this relation was P over T.
Which one?
Was not P over T. That one, I guess.
Yes. I have a v over there, so here I also have a v. Well, here, this is already PV over KT. This KT cancels this one, so this is 3 over 2 PV. Well, I already know what the pressure is. So the pressure is given by this one. So the 1 is our classical gas result, plus we have the correction. And then we can look for the specific heat. This is nothing but the derivative of U with respect to T at constant volume. This will be equal to 3 over 2 nkt, nk, this is the derivative of the first term. And from the second one we would get 3 over 2 nkt and k, 1 over 4 square root of 2 lambda cube over g times v. But keep in mind that lambda cube, now I have to take the lambda cube was t to the power minus 3/2. If I multiply it with t, it is t to the power minus 1/2. When I'm taking the derivative, there is a minus 1/2 over here. So CV is 3 over 2 and k 1 minus 1 over 8 square root of 2 lambda cubed over g times v. Now, compared with the bosonic case, so we will also calculate CV at the low temperature limit. You see, in the case of the bosonic gas, this was the classical limit. Well, the bosons at very large temperatures, they approach the classical limit, but from above. And they will increase as you increase the temperature. And at a critical temperature, you had obtained this cusp, this discontinuity in the derivative, so we have a phase transition over there. This was for bosons. Now for fermions, you see the specific heat as a function of temperature, there is a minus sign. So in the classical limit, at the very large temperature limit, the specific heat again approaches the classical result, 3 over 2 and K. But for not so large T, it is below the classical result. So this will just go below. And again, the general thermodynamics, the third law of thermodynamics, tells us that the specific heat should go to 0 at 0 temperature. So this will, just like the fermionic case, it will go to 0. We will see how it goes to 0. So there is no cusp, so it just monotonically decreases and it goes to 0. So this is basically what we have in the large temperature limit. Now we can go to the small temperature limit. Any questions on this large temperature limit? Well, you see, small temperature basically means that beta goes to infinity. Now, if you look at this term, which was 1 over e to the power beta epsilon minus mu plus 1. This goes to, okay, so if beta goes to infinity, and if epsilon is larger than mu, epsilon minus mu is a positive number multiplied by infinity is a positive infinity, so e to the power positive infinity is infinite, 1 over infinite is 0. So this number goes to 0 if epsilon is larger than mu. So none of the states that have an energy higher than mu is occupied. There are no particles there. And on the other hand, if epsilon is less than mu, you see epsilon minus mu is a negative number. If you multiply it with positive infinite, you get a minus infinite. E to the power minus infinity is 0. So that exponent in the beta goes to infinity limit just becomes 0. So 1 over 0 plus 1 is just 1. So basically we have a step function. So here mu 0 is the chemical potential at zero temperature, which is also identified as what's called Fermi energy. You see, in the case of the bosons, the chemical potential was always negative. In the case of the fermion, the chemical potential is at 0 temperature, it has to be positive. It kind of makes sense if you think about just, you have this gas of fermion, you start adding fermions one by one. You see, the first fermion that you add, the system will, in the 0 temperature limit, the system will go to its ground state. So you add one fermion, it goes to the ground state. Let's just ignore the degeneracy for the time being. You add one fermion, it goes to the ground state. You add the second fermion, It cannot go to the ground state because it is occupied. It goes to the first excited state. The energy of the system has increased because now it's in the first excited state. The entropy had remained constant because basically there is a single state with a one fermion in the ground state, one fermion in the excited state, and the entropy is zero. So if you remember in the case of the bosons, we had said that if you add one particle to our system, you have to extract energy from the system to keep the entropy constant. But here there's no such problem. At zero temperature, the entropy is zero anyway. If you add particles, if you add fermions, the entropy stays zero, whereas the energy of the system keeps increasing. And if you add one more fermion, then it just goes to the second excited state. And you just start filling your energy levels starting from the ground state. And you fill all the energy levels, you just put the fermions to all the energy levels starting from the ground state up to a level in which when you reach that level you don't have any more fermion left. So all the levels up to a given energy will be occupied. There will be one fermion, and none of the energy levels above that energy level will be occupied. So everything, there won't be any fermions that are in the above energy level. So that's basically what this tells me. All the energy levels are filled up to the Fermi energy at T equal to 0, and none of the levels above the Fermi energy are filled. So let's look at what this Fermi energy is. You see, the chemical potential is always determined by this equation. N is equal to G d epsilon A epsilon 1 over z to the power minus 1 e to the power beta epsilon plus 1. Now, at T equal to 0, the number of fermions is still fixed. This is G times the epsilon A epsilon, but this is now a step function. Now, A epsilon was proportional to epsilon to the 1/2. So if we evaluate that integral, this is G times 3. No, there's no G, sorry. G is already included in the density of states. 2/3 epsilon Fermi, A of epsilon Fermi, times, no, this is. This is what gives us the density of states. Now let's calculate what this A is. I have avoided it. I don't remember the expression. Let's just evaluate it. So A epsilon d epsilon is basically G times d cubed P d cubed Q divided by H cubed. So this is equal to G times V times 4 pi times P squared dP over H cubed. So P is square root of 2m epsilon. So A is G times V times 4 pi times 2m to the power 3/2 times 1 over 2 times epsilon to the power 1/2 times H cubed. This is G times 2 pi m kt over 8 square root of this one over H cubed. Now let's see what is missing. 2m to the power 3/2 is already here. Here I just have a 2 pi. Here I have 2 pi square root of 2. So let me divide by square root of 2 pi. No, sorry, it's 2m over here. Here I just have 2 pi. Here I just have pi to the 3/2. So here, so I have 2 square root of 2 pi V. Epsilon to the 1/2. So n is equal to V over 2 square root of 2 pi G over lambda cube epsilon Fermi to the power 3/2. Now here there's a 3. I multiply by 2/3. So this equation tells us what the Fermi energy is. Now there seems to be a problem, the units do not match. Can you see the mistake? A epsilon should have the unit 1 over epsilon, 1 over the energy. Now if you look at over here, V over lambda cube is unitless. A epsilon does not have the correct unit. Oh, yes. You see here, okay, there was a problem over here. Here I had introduced this factor k2 to the power 3/2. So I have to divide this thing by kt to the power 3/2. Okay, now it is correct. So n is 2/3 epsilon Fermi. A epsilon is g times v times 2 pi times 2m to the power 3/2 over h cubed. Epsilon to the 1/2, so epsilon to the 3/2. So epsilon is the density times 3 over 4 pi times h cubed over 2m to the power 3/2 over g, this g, to the power 2/3. This is the Fermi energy. Or this is equal to 1 over 2m times n over g, 3 over 4 pi h cubed to the power 2/3. Well, this quantity over here is defined as the Fermi momentum. So the Fermi momentum is n 3n over 4 pi g to the power 1/3 times h. Now, typical values for these parameters is the Fermi energy is typically of the order of electron volts, which corresponds to 10 to the power 4 Kelvin, the corresponding temperature. Now, the typical speeds, this is of the order of 10 to the power 6. So the electrons over here is moving at speeds typically 1% the speed of light. They're quite fast. Although we are at zero temperature, there is a significant portion of the electrons that are moving at speeds around 1% the speed of light. Now let's look at the energy of this system at zero temperature. The energy is not zero. Now the energy of the system will be just the epsilon times this from 0 to epsilon Fermi. Since we are at zero temperature, all the states up to epsilon Fermi energy will be occupied, none of the others will be occupied. This is equal to G times V over 2 times square root of 2 pi. No. G times V times 2 pi over 2 pi 2m to the 3 half. m to the 3 half and epsilon to the 1 half from 0 to epsilon Fermi. The epsilon to the 1 half times epsilon, so this will be GV 2 pi times 2m to the power 3 half epsilon to the 5 halves times 2/3. 2/5. Well, we can convert this somewhat, is the number of particles was given by this expression over here. So U is, you see here in the, let's put the N. Well, in the expression of N, we already have 2/3, but here we have 2/5, so we have to multiply by 3 and divide by 5. And then we have here we have epsilon Fermi to the 3 halves, but here we have epsilon Fermi to the 5 halves, so we have to add the epsilon Fermi. G is common, V is already there, 2 pi is there, here I should have an H cubed. Now this is the U. It has a huge energy in the ground state, basically because all the excited states are occupied. There are a macroscopic number of particles in the excited states, which gives the system a huge amount of energy. Well, we can look for the pressure. At zero temperature, since these are moving quite fast, they do exert a pressure. In the case of the bosons at zero temperature, the pressure just went to 0. But not for these. The pressure will not be 0. Well, let's calculate the pressure. We already know that in general, U is 3 over 2 PV. So the pressure of this system is 2/5 the number of particles times the Fermi energy. Now we also know the pressure. And in fact, this pressure By the way, if you try to understand the star formation, what stabilizes neutron stars is that there's the attraction, gravitational attraction, and that's pulling the neutron star inside. That's trying to collapse the neutron star, but the neutron star is not collapsing. This is the pressure that is responsible for it. So probably next week we will be discussing a bit about the neutron stars, how it is stabilized. Now this system at small t is large t. We have a non-degenerate fermionic system. And at small t, it's called a degenerate fermion gas. Now, of course, this pressure, the energy are all valid at the zero temperature limit. Now, the next thing we will do is what happens if the temperature is small but not zero. So what are the corrections to these expressions? Let's give a break now, and after the break we can continue.